Last time we met, we talked about these physics topics. We talked about the electric potential and potential difference in electric field and the path independence of the potential difference. Now, these things take a lot of practice to get intuition about, so we're going to spend some time today delving into the definitions and getting some practice thinking about them. So for today, we're going to review the definition of electric potential, and we'll discuss the potential at one point and how we could define the potential at one point rather than just a potential difference. And we'll talk about the potential inside of a conductor, as well as then the potential inside of an insulator. And if we have time, we will discuss the energy stored in a field. So can we define the potential at a single point? Okay, the main definition that we have for potential is about differences. It's about potential difference. And it says the potential difference is defined as the integral from point A to point B of negative the integral from point A to point B of electric field dotted into X. And this is a line integral, right? There's vectors in here, and you dot the electric field into the direction that you walk along the path. So what this means is that I take a step in a direction along the path. I take the electric field that's parallel to the direction I just stepped, scoop it up, put it in my pocket, take another step along the path, scoop up the electric field that's parallel to my direction and put it in my pocket, and I keep scooping it up, and the whole thing together gives me the potential difference between those points in space. We'd like to move on and think about the potential. What's the potential at one point in space? Can we define that? So here's physically how we're going to think about that. Give me 2 point charges, okay? Give me 2 positive point charges. And we already thought about the physics of these 2 point charges together. We said, well, you know, when they're close to each other, they really strongly feel each other's effects. When they're far apart, they don't feel each other's effects. So think, for example, about this positive charge being the reference charge. We're going to hold it still. And take this other point charge and move it close to it or farther away from it, okay? At infinite separation, send the test charge, you know, to Mars. All right, at infinite separation, that test charge doesn't feel the reference charge, right? There's no interaction between them. So we said the energy between those was 0 at that point. And then as I bring that point charge in from infinity to interact with this other point charge, now the energy of interaction goes up and up and up and up and up, okay? And in fact, as we did the same thing, the electric field has that same shape. So the electric field of this point charge has that same kind of thing. Off at infinity, the electric field is 0. And then as we get closer and closer to the point charge, the electric field goes up because it has this 1 over r squared law. We want to think about potential in the same way. So hold this reference charge here, okay, positive point charge, reference charge. And I want to think about the potential that the test charge experiences as it gets closer to the charge or farther away. So send the test charge off to infinity. They should feel nothing, right? So we'll say that that guy feels nothing out there, that whatever potential it's experiencing, we will define to be 0. Because that's the physically intuitive way to do it, such that when two things are infinitely far apart, they don't feel each other. Now, there's a mathematical way to do it as well. So the potential at a single point we'll define mathematically as the potential, VA, potential at point A, defined as, 3 bars means defined as, VA minus V at infinity. So look at that mathematics and tell me what must be true about V infinity, the potential at infinity, for me to be able to make that definition of the potential at a particular point. I have VA defined as VA minus V infinity. So I'm getting a big fat 0 from the back of the classroom, thank you. All right, so V infinity must be 0, right? If we define the potential at a particular point in space to be equal to itself minus the potential at infinity, the only way to do that is to have the potential at infinity be 0. So you can either think about this as a mathematical definition or the very physical definition of think about the potential exerted by a point charge. And if I go way off to infinity, I should not feel the point charge. So we define the potential at infinity as 0, and then everything else will be relative to that. Do you have any questions about the definition? Oh, yeah.
So when you have an infinite plane, then you just assume that you need to find the voltage.
Yes, OK, he just broke my definition. Thank you, I appreciate that. Let's think about the infinite plane. So you want a plane charge, right? So an infinite plane of charge, so a sheet charge. And then we can still define the potential at infinitely far from that as 0. It'll still work. So in that case, you have, in the case of the infinite sheet charge, we have the electric field is constant pointing away. But if I think of potential like height, remember we're making that analogy between potential and height. So then I just need to put that plane at the top of a mountain where the slope is constant going down from it. And then all the way to infinity, it's going to go to, no, it broke again. Thank you for breaking my definition. OK, so, yeah, that's such a good comment. OK, anyway, this doesn't work for the plane charge. Good question. So we're going to use this for point charge situations, not for infinite sheet charges. So very good. Thank you. All right. Any other stump the professor questions? That was excellent. Good. OK. Think of point charges. Thank you. All right. So the potential of a point charge. See, we're kind of ready. All right. So the potential of a point charge. We're going to think of this definition again, that delta V is minus integral from a to b of E dot dx. And the electric field of a point charge is 1 over 4 pi epsilon naught q over r squared r hat. And now I want to think in terms of, again, in the context of the point charge, if the voltage at a particular spot is equal to itself minus the voltage at infinity, well, voltage at infinity we already said was going to be 0 for point charges. So this is minus integral from infinity to r 1 over 4 pi epsilon naught q over x squared dx. So if I integrate, look inside this integral, and the only thing that depends on distance is x, right? So q, 4 pi, epsilon naught, those are constants. So integral of 1 over x squared is minus 1 over x. So the minus sign cancels that minus sign, and I get 1 over x. And I'll integrate that from minus infinity to r. And then plug in the r here, and I get 1 over 4 pi epsilon naught q over r, minus the contribution from infinity, which for the point charge case, we said we could define as 0. So there's minus a big fat 0 over here, like the back row told me before, minus a big fat 0. And so we define then the potential of a point charge as 1 over 4 pi epsilon naught q over r. So that'll satisfy this intuition of I have a positive point charge here, the reference charge, and I think about what's the potential hill that it's creating in space. Well, it makes a nice steep hill, and then that steep hill, we're going to say, goes to 0 at infinity. Do you have any questions about how that happens? OK, here's the graph of it. If I think graphically, then if this is a positive point charge, I like to think first in terms of point charges, of positive charges. So if this is a positive charge q, then this graph will just look like 1 over r. If I plot the potential versus separation, well, versus distance from the point charge r, it goes like 1 over r with this prefactor of q over 4 pi epsilon naught. And as I go infinitely far from that point charge, the potential goes to 0. And then as I come back, it blows up like 1 over r. Okay? Now, if I had a negative charge, I simply draw the same graph but put it on the negative side of the axis, flip it over, and make it negative. So for a negative point charge, it looks like this. And again, it extrapolates out to 0 at infinite separation. Do you have any questions about that? OK, so thinking in terms of our analogy between potential and height, if I think of this as like height, and let me put a positive test charge in here. So put a positive test charge right there. Let's say that I have a positive reference charge sitting in space giving me this positive potential. And I put a positive test charge in there and let it go. Which way is the positive test charge going to run? Which way is it going to tend to want to go? OK, I see some people hitchhiking this direction, right? So it's going to tend to run that way. It runs down the potential hill. OK? Now if I put it over here on this potential line, so put a positive test charge here, which way does it tend to want to run? Yeah, exactly. It runs this way because that's going to send it down the hill. OK? Do you have any questions about that? OK. Now this looks very much like potential energy, right? So in terms of potential energy, we had 1 over 4 pi epsilon naught q1 times q2 over r12, which is the separation between two charges. This is directly from lecture 8. So just to remind you that it's all making coherent physical sense, if I think about the potential energy between 2 point charges, right, that's just the potential times q. And so here's the potential you had, q over 4 pi epsilon naught r. That's the potential we had from the previous slide, times the test charge q2. Now I've got an energy. And the energy looks very similar when you plot it out. Okay? And this would be the energy in the case of attraction. Two attractive particles want to roll down that potential energy hill and come together. Any questions about that? OK? All right. Now, if we're thinking of potentials that are coming from point charges, as you pointed out, point charges, if I add up electric fields, right? Remember how electric fields went? We had a superposition principle. We said I could take any shaped charge you want, and I could treat it in terms of little point charges. And each of those point charges exerts an electric field throughout all of space that we said looks kind of like a dandelion, right? And then I could get the total electric field anywhere in space by adding up the electric field from all of those different point charges. Okay? Well, I can think similarly in terms of potential from point charges. Okay, I can think of, well, each point charge is exerting a potential in space. Each point charge exerts another potential. If I want the total potential, I can just add up the contributions from those guys. Okay, so if I think of each point charge as creating its own little mountain, it's like I put one point charge in and it makes a mountain, right? It makes kind of this height. We'll make that analogy between height and potential. And then if I add another point charge, it's like it builds another mountain on top of that landscape. I add another point charge, it builds another mountain on top of that landscape, and so forth. Okay? So that's one way to do it. I can just add it up that way. And either way works. I can either think of adding up the potential from each, or I can think of adding up the electric field first and then calculating the potential. Either way you want to do it. Okay? Any questions about that idea? Okay? All right. So potential and electric field are related, but potential difference and electric field, they're related by an integral equation or by a differential equation. So in the integral form, we had that delta V changes in potential. Okay, delta V is minus integral from initial to final position of E dot dl. Delta is always final minus initial. So this integrates then from initial to final spot, E dot dl. That's the integral form. If I know the electric field already, then I can take a line integral of a path along the electric field in order to tell me the height difference. If I think again in terms of mountain climbing, right, the electric field is like the slope at any point, and I take that integral, that gives me the potential difference of the height difference. Or I can take this equation, which is about an integral, take the derivative of both sides and get myself a derivative form of the equation. These are the same physics, just this is expressing it mathematically as an integral. This is expressing it mathematically as a derivative. Same physics, though. So in this case, we rewrite the electric field. This is from last lecture, lecture 9. We write the electric field as minus dv by dx, where we said x is a vector. And so what does it mean to take a derivative with respect to a vector? Here I've written it out in components, so you know exactly what it means. So here's what it means to take a derivative with respect to the position vector. That minus sign comes straight over. It's just a minus sign. But this dv by dx, where x is a vector, really means this. Where here I have a term that's in the x direction. That's what x hat means. And that term that's in the x direction is dv by dx. And then I have a term that's in the y direction, and that term is dv by dy. Have a term that's in the z direction, and that term is dv by dz. You see how I've changed the derivative from a d to kind of a curly d? All right, it's the Greek letter delta. So this means, this isn't scary, okay? Looks scary, but it's not, promise. It means a partial derivative. Here's what a partial derivative means, okay? It means think of the potential as some height landscape. So we're on some mountain range, okay? And I stand at one spot in space. What the first term means, what partial derivative of v with respect to x means is take a step in the x direction. As I go only along the x direction, what was the height change? That's all it means. What's the slope in the x direction? Write that down and put it there. So partial derivative means only look at the x direction for now and write that contribution down. Just means neglect y and z. And then I'll come back to where I originally was, and now I'll take a step in the y direction. As I step in the y direction, what was my height change? Okay, I go one step in the y direction, what was the height change? Write it down there. Okay, go back to the original point. Now take one step in the z direction, what was the potential change? Write it down there. That's all that mathematics means, okay? And we said we can summarize it as a gradient, minus gradient of v. And how do I know? So this is math, all right? But you should get a physical intuition for what does this vector really mean. And what we said, physically speaking, what this vector means is if I think about the potential being like a mountain range, if I think about, well, which direction will the gradient point, the way to find that out is to put a ball on the hill and let the ball go. whichever direction the ball rolls, that's the total direction of this vector altogether, right? It's x plus y plus z components will give you that vector that points in the same direction that the ball would roll. That's how you figure it out, okay? Or it's like water rolling down the hill. Do you have any questions about that? All right? And it takes a while to get familiar with this math not looking scary anymore and being much more physically intuitive, like walking around on a mountain range. Okay? So we'll get some practice with that. And remember what derivatives mean, right? So this is some function versus x, and this line here was some function. And a derivative is a slope. It's just the slope of this function at a particular spot. So what we're thinking of is the potential as this function, and then I want to take derivatives of it in different directions. So I'll plot out the x direction, and I'll take the slope right there. Then the slope again is rise over run, and then that gives me that contribution to the electric field. Okay? Do you have any questions about that? Okay? We'll get a little bit of practice with it. Okay, the question is the following. Does knowing the electric field at one point in space, and only that one point, allow you to calculate the electric potential at that point? So it's like I tell you, at one point in space, there's an electric field of 5 newtons per coulomb up. Does that allow you to tell me the electric potential at that point? All right, this is a hard question. You guys were about 50-50 split, and then after discussing, you got to be about 60-40 split. So this is a hotly debated topic. So tell me what you're thinking. What are the lines of reasoning that we need to draw out and analyze here? And you can always tell me your neighbor's line of reasoning instead of yours if you like. Yeah, right here. Okay, all right, so he's going to answer B because he knows we're given the electric field at one point, but we want to calculate electric potential. And to get this potential difference here, I need to go between 2 points. So he's arguing that I don't have enough information to solve the problem. All right, yep. OK, all right, so let me repeat that for the people in the back and tell me if I got it. He's saying we're just given the electric field at one point in space. We don't know if it's due to a point charge or multiple point charges. And so then if I think of integrating the electric field to get to a different spot, who knows how many other point charges are around influencing it, adding their own little mountains. And so as I do that, then it's hard for me to know. Is that basically OK? So you chose which one? B, OK. All right, yeah. What's something else we should consider? And then I'll get you. You were raising your hand, right? No? You're just waving, OK. OK, so that led you to which? OK, so you answered no because you're pointing out that to get the voltage, I need not just electric field, but I need some distance. I need a path to integrate it over. And I don't know that distance, so I have to answer no here. OK, all right, other things we should consider? What leads me to A? So far, people are just arguing for B, but can we think about what would argue for A? Yeah. OK, so she's pointing out that if I think in terms of the point charges, which is what we've been doing so far, I actually know the point at infinity. So you can use that extra piece of information that if this is due to point charges, the potential out there we defined as 0, and then you can integrate up and find it. So maybe you do have enough information. So you answer, or that's an argument that leads to A. OK. All right. So does knowing the electric field at one point allow you to calculate the electric potential at that point? To get potential, right, the potential is this equation here, that the potential at one spot in space is minus integral from infinity, right, the infinite separation, up to that spot in space, E dot dl. That's the potential. And so I need to think about integrating an electric field along that path. Okay, I've got the clicker question still open, by the way. We're still trying to figure out the answer. So remember the graphical interpretation of an integral. Okay, the graphical interpretation of an integral is that I'm going to take the area under this curve between those 2 points, infinity and r. So I've got some electric field, and it's going to go off to who knows what. Maybe it does go off to 0 at infinity. Okay, if I've got just point charges, that should be the case. But I don't know what it does all the way. I guess I shouldn't point over here. That's for you guys. If it's I don't know what this does out here. I just don't. So if I gave you only the electric field at this point, But what I need to do is take the area under this curve all the way out to infinity. Who knows what happens in between, right? There could be some other bump in the electric field. There could be another point charge that I encounter. I just don't know. And if I encounter another bump, that's going to dramatically change the area under the curve, right? So another way to think of an integral is like area under a curve. So this area I can't calculate if all you told me was this point. Does that make sense? If I think about the graphical interpretation of the mathematics, then just knowing that at this point in space I had a particular electric field of, say, 5 newtons per coulomb pointed north, that doesn't tell me the rest of the shape of the curve. So I don't have enough information to calculate it. Okay? So the right answer here is going to be B. Knowing the electric field at one point and only that point doesn't allow me to calculate the electric potential at that point. I don't have enough information. Okay? Okay, now I'm going to ask you the reverse. Because we have a derivative equation relating these guys, and we have an integral equation relating these guys. So the question now is, does knowing the electric potential at one point, and only that one point, allow you to calculate the electric field at that point? All right, again, it's a hotly debated question. All right, you guys are about 50-50 still on this one. So what are some things we need to take into account here? What's a line of reasoning that gets me to yes? What's a line of reasoning that gets me to no? And we'll tease them apart. What do we need to think about? What now? Oh, yeah. OK, all right, so I'll repeat this for the people in the back. He's using the equation on the right-hand side, the derivative form, which is that the electric field is minus the gradient of the potential. And if we think back about how we take that, right, we're thinking about the potential as height, and then we only know the potential at one spot. That doesn't tell me how the potential changes as I walk around, right? I have to think about how the potential changes as I walk around to use that equation. So that led you to answer which one? B? OK. All right. What's a line of reasoning that leads us to yes? How do we think about that one? Or another way to think about B. I just want to get the lines of logic out on the table and think about them. OK, so some of the lines of reasoning that might lead you to A is that, look, I have the potential, OK? The way that we wanted to go before was to go from field to potential, and that didn't work. But maybe you can go from potential to field. All right? That would lead you to A. Or thinking about maybe if I know enough about the point charges, if I just assume I have point charges, then there might be enough information. Maybe I can just assume that the voltage or the potential is 0 at infinite separation or something like that, and then work backwards. So let me show you some graphical things to take into account to try to tease this out. So thinking about the graphical interpretation of derivatives and integrals, we basically have one derivative equation and one integral equation. The integral equation was that changes in potential are negative integral from initial to final spot E dot dl. Okay? And the other equation we have, the derivative equation, is that the electric field is minus gradient of the potential, which we said the x term of that is minus dv by dx in the x hat direction, plus there'll be a y component plus a z component. So we need to think in terms of the graphical, at least it helps me to think in terms of the graphical interpretation of this mathematics. So think if I want to get the electric field, and it's a gradient of the potential, it's a derivative. So think of the potential versus the distance x like some function. I don't know what it is. But this right here, dv by dx, is the slope, right? So dv by dx is always a slope. And the slope right there, I wasn't given in the problem. If I'm just given the potential, if I'm just given that this point in space is at 5 volts, I don't know what that means, right? So I could keep this whole thing the same shape and move it up by 10 volts by just sticking a battery to it, right? So move it up by a few volts. So I could take the shape of that and move it up or down, and I'd change the overall potential, right? Believe it or not, I could take the whole universe and add 5 volts of potential to the whole thing, and you would never know. So what matters for calculating the electric field is the slope at that point. And just knowing that this is, say, 5 volts doesn't give me the slope. There's another thing to consider, too, which is that you were asked to whether you can get the electric field showing just the potential at one point in space. So not only does the value of the function not tell you the slope at that point, you need more information, but electric field is a vector, right? And if I just give you a scalar number like 5 volts, you don't have a way to get a vector out of that. But if I give you the potential landscape, you can get a vector out of that, okay? Because it'll be the slope of that hill in the direction that a ball would roll. So we need more information in order to get the electric field out. You have to have the slope. You need the gradient of the potential at that point. And then, again, thinking the opposite direction, right? Thinking about change in potential is integral E dot dl, or the potential where we integrate all the way out from infinity. Just to remember that is that the integral is always an area under a curve. So if I just know a single point, I don't know the shape of that curve yet. I can't get an area. And especially if I'm trying to integrate and get the area under the curve all the way out to infinity, that's really risky, right? Who knows what somebody else could put out there in the way? Road bumps, hills, valleys, who knows? And that'll totally change the area. You're familiar with the graphical interpretations of these, right? All right. So keep in mind then that when dealing with either the derivative form or the integral form, you can convert, but you need a lot of information. You need enough information to take a derivative, which is a slope. Okay? You need the form of the function. Or you need enough information to take the integral, which is the area under the curve. So just a single point won't help you. Questions about that? Okay. All right, now I want to think about what does the potential look like inside of different materials. So let's take a metal first. So let's think of a conductor or a metal, so a hunk of metal here. And I want to think about what happens to the potential inside the metal. What we know so far about a metal, and I drew a sphere up here, but it could be any shape, so think of any shaped metal. What we know about a metal is that in the interior of the material, what's the electric field? Do you remember what the electric field is in the interior of a metal in equilibrium? 0, yep, big fat 0. So, and the reason for that is that inside of a metal, the electrons act like a liquid. We actually call them an electron liquid. They can flow around. And if I think inside of the metal, and I think of an electric field inside, a net electric field, the electrons will run along the electric field. Okay? And they'll run along the electric field and build up an excess charge, which then exerts an opposite electric field and cancels it out. And in fact, the electrons will run around until they've made it such that they can't run around anymore, right? And then at that point, once everything reaches equilibrium, it's because there's no net electric field inside anymore. The charges distributed themselves so as to let everything come to equilibrium. Okay? So in the interior of a metal, there's 0 net electric field. So we want to think about what that means for the potential. If the potential difference is the integral from a to b of the electric field dot dx, and the electric field in the interior is 0, right? So what's the potential difference in the interior? Okay, so the potential difference must be 0. If the potential difference is 0, then V is constant in the interior of the metal. So 0 net electric field in here means that, you know, if it's 5 volts over here, it's 5 volts over there, it's 5 volts over there. Now, I could even think of bringing another charge into the scene, right? So let me bring in a point charge, a positive point charge here, that's exerting an electric field. Well, the metal responds by moving its charges around until it can't move the charges around anymore, right? So it moves around until there's 0 net electric field inside, and that's actually called screening, right? The metal screens the net electric field out of its interior. And so equilibrium is that equilibrium from metal is when the electrons stop moving. It's that the electron C has net 0 velocity. A metal's out of equilibrium, for example, if you were to apply like a current or something like that. So if I think of hooking it up, then we have to redo the calculation. Or immediately after applying an electric field, right? When I first bring the electric field in, the charges can move around. But that happens super fast. That's like 10 to the minus 12 or 10 to the minus 13 seconds. It's really, really fast. Do you have any questions about this idea? Okay. Inside the interior of a metal, the potential is constant. Could be 5 volts, could be 20, but it's constant. Okay. Questions? Okay. All right. I want to think now about the potential differences and what the potential looks like inside of an insulator. Okay. The metal was one way to do it. And in an insulator, so here's the situation I want to set up. I want to set up a capacitor. So here on the left-hand side, I have a positively charged sheet. And on the right-hand side, I have a negatively charged sheet. And in the interior, I'm going to fill it with some sort of insulator. Maybe it's styrofoam, maybe it's glass, maybe it's something like that. And inside then, the little dipoles in the material are going to orient. And then maybe from that, I can kind of try to figure out, well, what would be the potential difference inside the insulator? But let's see here. If I think really microscopically about what's going on inside the insulator, all right, I get these little polarized dipoles, and each dipole, out of its positively charged side, electric field comes out of the positive charged side, comes back into the negative charged side. So for example, look inside this dipole here. It's got a positive charge on the right and a negative charge on the left. So inside that dipole, the electric field points away from the positive charge. Okay? But in between two dipoles, the electric field points the opposite direction, right? It's got to always point away from the positive charges. So this is complicated, right? Each dipole is going to give me some sort of looping back kind of electric field, a dipole electric field, all right? But then I have to add all those up in the material. And this is a mess, y'all. We don't want to do it, okay? So in physics, there's often 2 or 3 ways to think about things, right? Doing it this way is possible, right? I could even think, well, maybe I'll just average over 10 dipoles and get myself an average electric field. You could do it. It's just really hard. So it's kind of like if you want to attack a castle. Anybody attacked the castle lately? Oh, come on. Who plays video games? Yeah, all right. Okay. So anyway, if you want to attack a castle, there's this straightforward way to do it, which is you take your battering rams and your catapults and your army and you approach from the front. And of course, they see you coming and they defend and they pour burning oil on you and things like that. That's the hard way, okay? It can work, maybe, if you put a lot of effort. There's the other way, the sneaky way, which is where you dress up as a washerwoman and you sneak in the back door and attack that way, okay? Physicists excel in finding the sneaky way. This is the hard way, okay? I'm going to show you a sneaky way to calculate the average electric field in there, which is going to be easier than that method. This will work. It's just really, really hard, okay? It's like taking a battering ram on the front door of a castle. So the sneaky way to think about it is the average field. So I'm going to think of an average field inside here. And I'll start from the outside. So let's go on the outside. So here's our polarized insulator. I just want to think about the polarized insulator. So it's polarized such that the positive charges have shifted to the right, the negative charges have shifted to the left, and along the right side of the material I have net positive charge, and along the left side of the material I have net negative charge. The electric field inside is complicated, but we can kind of figure out what the electric field should be outside. Okay? From the outside of the material, I have a net negative charge here, and so I should have an electric field pointing away. And from the outside of the material over here, I have a net negative charge, and so I should have an electric field coming in. So from the outside of this insulator, it should basically look like there's an electric field coming out of the top. It must loop back around and come back in the backside. Okay? So we can figure out what the electric field looks like outside. It's not so. Does that make sense that that's what the electric field looks like outside? Okay? Now, if I think in terms of the height analogy, so think in terms of potential is like height, and this electric field is like a gradient going around it, right? So if I know what the electric field is outside, it circles back around. I can take this line integral of E dot dl as I go around the outside. And then that would give me, I could go from point B, right on the top of the material, take the line integral around the outside and get the voltage difference between A and B. And the voltage difference is path independent. It will give me the exact same thing as if I had gone through the material, which is, we already decided was too complicated to go straight through the material. This is like taking the battering ram to the front doors of the castle, right? This one is like dressing up as a washerwoman and sneaking in the back way. So you can see that if the electric field comes out of the top of the material and back down around there, if I think of taking this integral, right, the path integral of E dot dl along that path is, well, I take a step, I walk along, I take the electric field parallel to my direction, scoop it up and put it in my pocket. And I'm going to take another step, take the electric field, put it in my pocket, and add that up all the way around. That'll all together give me the total height difference between here and there. And you can see that the electric field is going to have a parallel component to my path the whole time, right? All along this path, I have a parallel component. I don't have any negative components. So I'm going to be all together scooping up something here that's positive. Now, again, the height, whatever height difference I get from here to here, has to be the height difference I'll get if I march through the entire material. It's just that going inside the entire material has these steep valleys, steep mountains, steep valleys, steep mountains. Who knows what's going on? And then at the end of the day, I get the same height difference. Because remember, they're path independent. So anybody see the movie Inception? Okay? There's a concept like that in Inception.
Cobb said you'd be back,
I tried not to come, but
but there's nothing quite like it.
it's just pure creation.
Shall we take a look at some paradoxical architecture?
You're gonna have to master a few tricks if you're gonna build 3 complete dream levels. Excuse me.
What kind of tricks?
In a dream, you can cheat architecture into impossible shapes. That lets you create closed loops, like the Penrose steps, the infinite staircase. See? Paradox.
So the clip from the movie is about this staircase that you can't really make, right? Or maybe you've seen it in an M.C. Escher drawing where it looks like there's a staircase that spirals back and meets itself, meets the same level. That's not possible, right? But we do know that voltage has to do that, right? Potential has to do that. Whatever the height is as I move around, as I come back, I need to get back to the same height, okay? So a real staircase couldn't meet itself, right? But I'd have to have it come down and then have some steps that go back up again, right? So that's physically what has to happen. They have to meet each other. So that's the idea behind this. If I know that in going this way I'm hiking down the hill, then whatever complicated things happen inside here, I know that the height difference between those is the height difference, okay? I'll get the same answer no matter which path I take, no matter whether I go outside the material or inside the material, all right? And if the electric field's pointing out this way, all right, which one of these voltages is the greater voltage? Is the potential at A or B greater, given this? Okay, B, I'm hearing a lot of B's. That if I think of this as how would a point charge move away from this, the point charge would roll down the hill, right? So the point charge would roll down the hill, so voltage B is the greater one. Do you have any questions about that? Okay. Oh, there's the greater than 0 appearing on the slide. Okay, all right. Now, the response of the insulator can be characterized by a dielectric constant, right? So here's the idea of a dielectric constant. I take that insulator, okay, and I know what the insulator is going to do, right? I apply a field on the insulator, dipoles happen, right? The dipoles exert some sort of average field in the material. We said it was hard to calculate, but we got it by going around the outside of the material. And then we can calculate the height difference, the potential difference across the material. And then from that, we can calculate the average electric field in the material. And so by doing that, we learned that inside the medium, the net electric field is a little bit reduced from what you applied. So I take some insulator, I apply an electric field, the insulator polarizes, and it polarizes so that in its interior, the net electric field, the total average, right, average over, say, 10 atoms at a time, that's going to be reduced. And it's reduced by a factor called the dielectric constant K. So I apply an electric field. Whatever the material is has some number K associated with it, the dielectric constant. And so then inside the medium, the net average electric field is the applied field divided by K. The bigger K is, the more it dampens the field. So if I have a big K, that means a large polarization, a large response in the material. And it also means that the net field inside is smaller. So here's my mnemonic for remembering what dielectric constant means, right? What did the dielectric constant say to the electric field? It said dielectric field, die, okay? So if you have a dielectric material, in its interior, it responds so as to weaken the net electric field inside of itself. Dielectric field, die, okay? That's what dielectric constants do. Here's some dielectric constants just to give you a feel. Vacuum, of course, is 1 by definition, right? If there's nothing around, nothing happens to the applied field. Air reduces the net electric field just a little bit. Plastic by a factor of 5. Water by a factor of 80. Something called strontium titanate by a factor of about 300. So if you want to really get insulator, strontium titanate. Okay, we're done for the day. We'll do that stuff next time.
Thank you for everything.
Okay.
Bye-bye, boys.
Have fun storming the castle.
Think it'll work?
It would take a miracle.
Bye-bye.